Hey guys, Evan here. For the last part of our heat diffusion for part C, okay? So as you remember, for the first part, we derived the Craig-Nicholson equation using our previous heat diffusion equation that we derived from the video before. So we used that and found the heat diffusion equation for Craig-Nicholson, which is this equation represented up here. And now we will use the von Neumann method like we did last time as well to basically figure out how the Craig-Nicholson method basically makes everything usable. You can use any number of R, it doesn't matter. You can use as big or as small as you want, R will still work. Okay. So let's find that out. So remember, Euler's law, it states that epsilon E of Ix is equal to cosine of X plus sine of X. Okay. We derived this equation to make it, we derived this equation to basically find cosine of X by itself. And once we figured it out, we basically say that cosine of X, if you remember from the last video, is just equal to epsilon I of X minus plus epsilon negative I of X, we delta X. Delta X y by 2. This is what cosine is equal to, okay? So you remember this, we can use this expression to plug in to all the temperatures here as well, okay? So let's get started, okay? So we know that we want to have temperature at position J of n plus 1 and temperature at position J at just n factored out from both of these expressions. So let's do that, okay? So we work on the left-hand side first. So left-hand side, if we take out the T of J of n plus 1, that leaves us with 1. Is that 1 plus 2R, right? Then inside the next bracket would be your first point of Tj plus 1 of n plus 1. And if you remember, we stated last time that T of J plus 1 is just equal to epsilon of I. We incorporated K delta X, and then J minus 1, so I was going to do it now, so later, is equal to E of negative I K delta X. Okay. So now let's use those and plug that in. Okay, so we start with T, temperature at position J plus 1 of n plus 1. Of this, we're almost right here. This temperature here would be n plus 1. And that factors out all the n plus 1s as well on the top of here. So all the n plus 1s gets factored out to this here. So now we have, oh, I'm sorry. I'll get there. Let's keep working. We're good. So we have epsilon of I K delta X minus plus epsilon of I K negative I K delta X, then plus 2. Okay. Oh no, I'm sorry. Maybe minus 2. We just factor out. No, that's right. Be plus 2. Okay. So this is the left-hand side here. Now let's do the right-hand side. Right-hand side. Let me try to adjust the light. Okay. I can adjust the lighting. It's gonna be a kind of a glare, so I'm gonna make the letters kind of bigger so you guys can see, hopefully. Like I said, left-hand side is the temperature at position J of n plus 1. And then brackets 1 plus 2 T of R of epsilon of I K delta X plus E a negative I K delta X plus 2. Okay. I just be minus 2. Minus 2. All right. So then the right-hand side, so we equal this out. Again, we're trying to factor out the temperature at position J of n. So right-hand side, we're starting with T. Position J of n And this would be times, again, 1, this is time to be minus T of R, 2 of R. Actually, where are we getting to? There's no 2. This would be R. This side would be R. Sorry for the incorrect. This side is R. There's no 2. Okay. 1 minus R. And inside the brackets, same thing as this side, and be epsilon I, K delta X plus E negative I K delta X minus 2. Okay. All right. Now, if you remember, like we stated here, this is equal to cosine. This term here is equal to cosine. So we can plug in cosine of X for both of this, the left hand and right hand side. So that would give us temperature at position J of N at time N plus 1 times 1 plus R of cosine of X, maybe 2 cosine of X minus 2 is equal to T temperature at position J at time N of 1 of R times cosine, 2 cosine. Cosine of X minus 2. Okay. From here, we can factor out the 2. And this is where I'm supposed to put the 2R. Okay, so T J of N plus 1, 1 plus 2R of cosine X minus 1 equal to T of J N of 1 minus 2R cosine X is 1. Okay. All right. Now, next thing we would do is that we want this, like we remember last time, the temperature at J of N plus 1 by itself. So we would divide this expression right here to the other side, to the right hand side. So this will give us that temperature at position J of N plus 1. This will be equal to temperature of this in J of N times 1 minus 2R of cosine X minus 1 divided by 1 plus 2R cosine X minus 1. Okay. All right. No, this was right. Okay. Sorry again. What's the last thing that I did? Because I remember we did this. I messed up here. This is plus. So this side is positive. Yes. So this side is positive. All right. So this top here is positive. Okay. Okay. Now from here, we would take out negative. So take a negative out. So equal out to, so y'all can see, temperature at position J of N times 1 plus T of R of cosine X negative 1 minus cosine of X divided by 1 minus 2 1 minus cosine of X. Hold on real quick. I'm gonna check my notes. I think I messed up somewhere. Okay, we're good now. One thing I made a mistake on, which I just caught now, because I was working through this and it didn't make sense. So the signs for 1 plus R and 1 minus R need to be flipped. So this on the left-hand side is actually 1 minus R, and this on the right-hand side is 1 plus. That's why I was kind of getting confused about the signs, because it wasn't really making sense. But, yeah. So now here, the top is 1 plus 2r cosine of x minus 1, and the bottom is 1 minus 2r cosine of x minus 1. I mean, plus 1. Yeah. Okay. And this should actually also still be minus 1. So yeah, we're good. We are good. This is a negative 2. And now we are good. Okay. All right. So now from here, we just take out negative, and then we get T of n of 1 plus 2r of 1 of T temperature at position J at time n at position time n is times 1 plus 2r of 1 minus cosine of x. And then we also divide by 1 minus 2r, 1 minus cosine of x. Okay. Now, if you remember that this expression here, 2r of 1 minus cosine of x, is actually equal to y. So our y is equal to t of r, I mean 2 of r times 1 minus cosine of x. So we can actually plug in y for the terms here and here as well. So let's do that. Let's do that, simplify the equation. Okay, so this will be equal to now T of n, position J times 1 plus y divided by 1 minus y. Okay. All right. Now from here, what do we do next? Next steps that we do. Okay. Perfect. Okay. So from here, we're good. We know from the y here, let's take a little bit backtrack. We know from the y here that the domain of this is -1 to 1. Okay. Now, if we take this expression of y of 1 plus y and 1 minus y, and we plug in 1 for y, we will get that. You'll get 2 and 0. Okay. Which is both our y's if we just want to do the domains, because these are basically the domains for the y's for the expression. So we want to do the domains of both of these. And we added 1 for both sides and -1 for both sides. We will get a domain of 0 and 2 and -2 and 0. So the y's here just represent what we just did up here. But we don't worry about the 0, but we worry about the 2. Okay. So we can actually plug in 2 for the 1 minus cosine of x. So we can represent y as 2 now. Okay. So now we can just put in here T of n, T of, yeah, time in, right, position J, times 1 plus T of r times 2 divided by 1 minus 2 of r times 2. Okay. And then we factor the 2's in. That will give us just, I'll put up here so I don't got no anymore. But that will give us T of n, just in J, at 1 plus 4r, and then 1 minus 4r. Okay. So this is our expression here, and this is equal to T at n plus 1, position J. Okay. So this is the expression here. And if we just plug in an r value, you will see why this works. Okay. So let's say our r is equal to 5. So let's do an example. Let's get a different mark. This is not. Let's see this works. Oh, perfect. I think it's also a reason why you guys couldn't see that well. My marker was kind of dying out on me. So let's say R is equal to 5. Okay. For our example. Okay, everything else. That's all right. So we're use expression of temperature n plus 1 with respect to J is equal to T at J n of 1 minus 4R 1 plus 4R. Okay. So we plug in 5. For this, we will get 1 minus 4 of 1 minus 4 times 5 divided by 1 plus 4 of 5, 4 times 5. Okay. And this is odd. It should be less than 2, less than or equal to 2. Okay. Because remember, we still use 2 for our domain for this expression. That's how we got this. That's what we got here. Okay. So this should be less than or equal to 2. Okay. So when you do the math here, you'll get that this is equal to 20 minus, so it'd be negative 19 divided by 21. All right. And this would be absolute. So this has to be absolute values. So this would be our expression here. So we get absolute value of negative 19 divided by 21 would be less than negative 2. And that is correct. That is true. And you can plug in any number. You can plug in 2, 3, 7, 11, go all the way up to infinite and infinite R's. And this expression will still be true that any R is less than or equal to 2. And you cannot change that. And this is why the Craig-Nicholson method works for any R method, any R number that we put into our system. Okay. So that's basic, that's the basis in the von Neumann for Craig-Nicholson. Hope this makes sense and explains more for the Python. Remember that we did for our first time, we did like a 0.495, and then we did a, what was it, 0.05. But that's besides the point. But hopefully this helps out more, better understanding of why we use Craig-Nicholson for R's, because with the other method, we were limited to what the R could be, but now we're Craig-Nicholson, we can use any R, it will work because it's an average. Okay. So yeah, that's it, guys. That's the end. Hopefully this helped you guys out, and I'll see you guys on the next video. Hey guys, Evan here again with another video. Today we are still covering the heat diffusion equation, but today we're doing it between we're using our algebraic, we're using the heat diffusion equation that we derived in our last video and then we're using the Craig-Nicholson method to actually derive what our new equation will be for heat diffusion. And then we'll plug into Python, have a code it out, and then we see a applied version of how it will look like and how it differs from our original diffusion question to our Craig-Nicholson. Okay. So first, how do we set it up? Okay. So we will start from the heat derivation that we started off with our last video, which we have the derivative of temperature respective time is equal to our alpha times the second derivative times temperature divided by the derivative of position squared. Okay. So now, if we remember, this equaled out to, when we went to our algebraic form, this went to the temperature at position time n plus 1 at position J minus temperature at position J at temperature at time n divided by the difference in time, the left-hand side, is equal out to alpha times, we get our temperature at J plus 1 respect to n minus 2 at the temperature at position J at temperature n. You all see? Let me make this a little bit bigger so y'all can see. At T J plus 1 n minus 2 of T at position J at time interval n again, and then plus, and then temperature at J minus 1 at position n. Okay, and this is divided by the difference in position squared. No, the difference in distance squared, okay? All right, and remember that we put an R term here in place of the difference in temperature, alpha, and the distance. We'll get to that later, okay? Now, from here, we will now incorporate our Kraft-Nicholson method. So for our Kraft-Nicholson method, we are trying to basically average out the equation. So average out average out both sides. So what would we do? We're trying to average out the block, basically. So far, you can the block, we're trying to average out. So what we're gonna do here is that we're gonna take this equation, and what we do, we'll keep the left-hand side the same. So it's to be temperature, addition J at n+1 time minus the temperature, addition J of n divided by difference in time is equal to alpha. Now to average it out, we have to divide the terms by 2. Okay, so we divide alpha by 2, and we'll make our brackets. We do temperature at J +1, and so this all stays the same. But now we will incorporate the n+1 term variable for temperature as well inside this bracket. So now we'll add plus, and this will now be the temperature at time n+1 at in our position J +1 minus 2 of temperature at n+1. I mean, at temperature at time n+1 at position J, and then plus temperature at time n+1 it's at position J -1, and this would be divided by still the distance in between the blocks, okay? So this is now the Kraft-Nicholson method. This is the Kraft-Nicholson equation. So we're averaging out this position, the time at n+1 and the time at n to find our equation for Kraft-Nicholson, okay? And what we'll do to simplify this, we will move this side over here. We will take the Tn of position J, move it to the right-hand side, and then now we will use the R, like I said earlier, and we're going to make R equal to alpha times our difference in temperature, time, like we did in our last time we incorporated R. But now this time, we will add 2 times the distance of the blocks squared, okay? This is our new R, okay? So now let's simplify our equation, okay? So let's start with the left-hand side. We start with this TJ temperature at time n+1 at J +1, okay? Remember, all this, every single term here is multiplied by R, okay? So we're just subtracting R times T temperature at n+1 at J +1. So we're gonna start with negative R at temperature n+1 at J +1 plus, and now you see we have temperature here and we have temperature here, okay? So what we're do is that we take the temperature out of both the brackets. If we put it to this side, we're not going to smudge them together. We're going to, because it has R, remember, we get multiplied by R. So this would be 1 for the left-hand side already of temperature at J plus n+1 at temperature at J, position J at temperature at time n+1 plus to R at temperature at n+1 at position J. And then minus R at temperature n+1 at time n+1 at position J minus 1. Okay. This is what our left-hand side looks like. So now let's incorporate our right-hand side, which would be now this expression left, and also this temperature at position J at N. Now we're moving over as well. Okay. So this whole side would be equal out to we'll start right here, the temperature at J+1 at time N. That'll just be R at temperature at J+1 of N. Okay. Next, we will have the -2 Tj of N. Remember, these are both the same term of temperature at position J of N. So what we do, same thing we did here, parentheses, so either plus parentheses of +1 minus 2R. And then this would be temperature at position J of N. And then our last temperature term here, plus temperature at J-1 of N. Okay. So this is our full calculation. This is our full, the right hand side usually guys know. This is our full entire calculation equation. Okay. This is it. This bad boy is it. All right. This is it. So you want to represent this on the block. So let's put out the blocks so you guys can further understand this. We have to do a little bit more. So we have the equation, but let's try to understand how it'll look like and how we'll actually incorporate this in the Python code. Okay. So we have our uniform block that will get heated on one side and on the left-hand side and the right-hand side. Okay. All right, so we have. This is representative position. So this is temperature at initial temperature 0, you have T1, T2, T3. So temperature at position initial position T0, temperature at initial 1, temperature at initial temperature 2, at position 2, then temperature at position 3, and then so on until we get to a temperature of Tn, which represents the temperature as how many blocks we have in total. Okay, so this is just position 0, 1, 2, 3, and then we represent this at the end as N. Okay. So one thing that we do know, so one of our knowns here is that the temperature at initial 0 and temperature of N, we already know those temperatures. Okay, because remember, this block is uniformly heated, so this has the same temperature throughout the entire block. Okay, but then at time 0, we start applying heat to both these blocks. Okay, so we can say this block will be 40. You put heat on 40 degrees Celsius and 80 degrees Celsius. Okay, so we already know the temperature of what those two blocks will be at the end. So these are both known. Okay. But past initial past time 0, we do not know any of the blocks in between here. So this right here, all the blocks in between temperature at initial temperature at position 0 and then temperature at position N, we have no clue what the temperature will be. Why is it? There we go. I don't know why Zoom does this. Okay, so we represent this as N-1. And I'll explain a little bit later. Actually, I'll just come back to this later. This is our first unknown. Okay. That's not all. We also have a second, we have a second unknown for this, uniform bar. That, let's say we start at position 0, okay, like we said. So at position 0, we apply this equation, we start with the left-hand side first, this would be at position J. So we start here at temperature 0, at position 0. We use this equation here, 1 + 2R at temperature at position 0, okay? But what if we have the temperature at position 0, but we have J minus 1? Well, this would be right here. Now you have a problem. Because this is now outside of the block. Okay, this is outside the block. We don't really need that, but we do. This is important because we still have to apply this for our equation to average out the bar for Craig-Nicholson. Okay. So now this here and then this division here, when we have T of n and we plus T of n, well, that would be n plus 1. We don't need n plus 1. But we need n plus 1, but it's outside the bar. So this is ours. So these 2 points here are our second unknown. Okay. So now for this will be represented as this. The blocks inside will be represented as n minus 1. For a number of blocks of the bar minus 1. And then the outside will be the number of blocks plus 1. So now we have n plus 1 and n minus 1. So now how do we find our unknowns? Well, this equation is a matrix. Kind of like we did for our part B video, our second video, our heat diffusion equation is a matrix. Okay, so this will be applied as a matrix and we calculate this out. So we can actually find these 2 unknowns using our matrix method. So let's build our matrix and I'll explain furthermore how this goes. So now let's build our matrix. So we're going to use the Craig-Nicholson equation that we had. Now I can restate this actually because you guys can't really see the board. This R or T then J plus 1 plus 1 minus 2R T J then minus 2 no, minus T J minus 1 and that's it. Okay. Well, you guys cannot see that. There we go. There we go. I just realized you guys can see. So let's build our matrices. So we'll have our left-hand side. So this is represented here. Okay. And then we have our temperatures. And then we have our products. We will give you. Okay. And then let's say we T1, T2, T3, and then this just goes all the way down to T of it. Okay. So then we have a point. So let's get started. All right, let's make it bigger. Let's start with temperature at position 2, because it'd be a little bit easier and you guys can understand a little more where I'm going at with this. Okay. So okay. So temperature this is like I said earlier, this is the left-hand side, right-hand side. Okay. So temperature 2. Let's start with the temperature U. That's our representation. That'd be at position J. Okay. So at temperature if we're representing that as where we start at in the middle of our 2 blocks here. We have our 3 blocks. Okay. we start out position two, this would be represented as position two here, okay? This would be 1 plus 2r, okay? So we're representing this as 1 plus 2r. All right, so then the brackets in between. We'll use this and put it here for this matrix, okay? For position T plus 1, we have negative r. So this right here would be negative r. And then our temperature at position T, position 2 minus 1, that'll also be negative r. Okay. All right, and we go to product side. Same thing. So start in the middle. We have our temperature 2, temperature at position 2. Here, that'll be 1 plus r, 1 minus r. So that'll be 1 minus 2r of T of 2. And you can represent this the product side. You can put J, or you just put 2, what it actually is. Okay. And then we have plus R of T at J plus at 2 plus 1, so 3 at time N. And then plus temperature. Oh, this is a plus. It should be a plus. Plus temperature at J. No, at position 1, because 2 minus 1 is 1 at N. Okay. So this will be how equation goes. The rest of it here, this would be zeros. So everything else would be zeros going out because we're representing 3 blocks here. Position 1 and 2, 1 and 3. Everything else would be zeros. Okay. So now let's do temperature at temperature at position 1. Okay. So again, now this would be 1. Okay. We have position 1. Then we have position 0. We have position 2. Okay. So our temperature at position 1, start here. That would now be 1 plus 2r at this block. On the right, 1 plus J, this is temperature at position 1 plus 1, that'd be negative r. And then 1 minus 1, well, that'd be out here. That'd be outside the matrices. Kind of like what we said earlier, our unknown. We have to represent this as negative r at T0. Because we still have to use that. That's still part of our block. This is important. We still need this, but it's outside the matrix. So what do we do with this? Well, basically, what we would do is I will move the negative r at temperature position 0 over here. So now inside this matrix, we will have plus r at temperature at position 0. So this term here, that's outside the matrix, this gets added, just is moved over, added to this side. Okay. So now that's basically it. The rest be zeros. All right. So now for our product, represent this as temperature at 1. So we would start off with T plus J plus 1. So that'd be temperature, so that'd be R times temperature at position 2 of N plus 1 minus 2R at temperature of 1 of N. But then we also run to the same thing. We have temperature at position 0 of N. But now we're just added into the product. So now we have 2 R we have 2 R's. Like I'm saying, we have 2 R times temperature at position 0 in the product. So you could say we have two times R temperature initial 0, or you can just leave it like this. This is also correct. But yeah, that's basically how it goes. For the third block, I mean for temperature at position 3, it would be starting here, it could be 1 plus 2R. If we do plus 1, it'd be negative R here. And then minus 1, we have position 2, it's negative R. And then everything else is zeros. All right. And then same thing, maybe the same expression just like this. No, of course, no R plus T0, but everything else will be the same, just go down the order. And then last thing I want to, there's two last things I want to say. So at T of N, we kind of do the same thing like we do for T of 1, okay? So at the end of our block, okay, here, we have N minus 1, N plus 1. Okay. At the end, we'll have, we'll have R1, 1 plus 2R. I represent this. Oh, that'd be matrices sideways. Then at the end, we'll have minus R again outside the matrices. So what we would do, just like we did at temperature at position 0, we'll add plus T of N plus R T of N onto the product side. Okay. That's all we're doing. That's really how we solve our two unknowns. The middles, they're exact same. They will stay the exact same throughout the entire time. You know, they just, the negative R's, the 1 plus 2R, the negative R, just keep shifting over order, depending on the position. So these will all still be the same thing, which is great. So they stay the same. They'll just keep shifting orders, based on position, and the product will keep going, will be the same as well. You just add a 1 to each temperatures, but the remaining constants will be the same. And then for our temperatures at position 1 and our temperatures at position N, you just have to bring over an R plus Tn at position N and R plus R times temperature at position 0 to the other side for the product. And that's really it. It's pretty simple. Pretty easy to understand. We will go over this more a little bit in the Python so you can actually see how this is done coded and what the plot will look like, will be out, look at. The plot will go up. I can't talk, sorry. How the plot will create, will plot out. But yeah, this is it, guys. Hopefully this helped. I know there was some lighting issues for me. I don't know why I keep doing this. But yeah, that's it. Hope this helped. I'll see you guys over on Python. This is now the second part, or the third part of the part C. The part C, equation. The part C, Crack-Nicholson heat diffusion equation that we worked on the whiteboard earlier, and we use a von Neumann and also the stability check as well. And now we're just playing all this on Python. Okay, so what we have here, we're supposed to simulate the time-dependent response in uniform bar initially at 20 degrees Celsius. After ends are raised, then maintain at 40 degrees and 80 degrees Celsius respectively. We're supposed to discretize the bar within 20 time-dependent temperatures and solve the equation for part C1 using SciPy linear algebra solve, pound banded, which is just a Seeger's matrices. And then for R, we know R is equal to 2 and over 200 time steps, and then plot the simultaneous results in 10 time step intervals. Okay, so it sounds like a lot, but once we start, you'll see it's not that bad at all. So let's get started. The libraries we'll be using on the left will be import NumPy. We'll use NumPy, SciPy for the linear algebra solver, and then we'll also be using poly.subplots and make subplots. Okay, so now let's start. All right, so let's first put into our initial values that we know. So like we were told, we know that our temperature on the left of the bar will be 40 degrees Celsius. Okay, the temperature all the way to the right of the bar, which is this right here. So we have our left T initial, which we know is 40. Our N, I'm going to represent here, is our T right. Which would be 80 degrees Celsius. And then we know that our middle here, which would be, we can say T initial is equal to, we need to do NP out full, is equal to, so we have a shape of M, of n, and then we'll do 20. So we know we have 20 time dependence. Okay. Oh, let's say yeah, n. Okay. And we also know that n is 20 degrees Celsius. Okay, so n represents the number of time dependent temperatures here. So it's be equal to 20. And then the 20 here is the 20 degrees Celsius that we have represented in the 20 time dependent blocks inside the uniform bar. Okay. And we need to make sure these have a period at the end. So they are float points. All right. And then lastly, we know R is equal to 2. Okay. So enter is all our initial values. So now let's go to this big equation here, our main equation, and let's start working this one step by step. So let's do the left-hand side. So the negative R times temperature J plus 1 and N plus 1 all the way over to the equal sign. So let's do our left-hand side. All right. And this right here, the left-hand side is represented in our diagonals that we did earlier. So like we said earlier on the whiteboard that we know that the 1 plus R stays as the 1 plus R's and negative R's on the left and right hand side are all diagonal, and they will always be diagonally the same. So the more steps you take, they'll just shift over diagonally. So they're if you put in the matrices, it'd be diagonally like that. So what we will need to do, so you need to basically plot this and put this in our Python. So how we would do this is that we can say our diagonal. So we start with the left-hand side. So the TJ plus 1, a negative R TJ plus 1. So we do the first diagonal. Diag is equal to, and this will be, it'll be the negative R times, okay, so now that we have our initial temperature, our initial values plotted, let's do the left-hand side of our equation here, which is the negative R temperature at position J plus 1 at time N plus 1 plus 1 plus 2R, a temperature at position J of N plus 1 minus R times temperature of J minus 1. Yeah, time N plus 1, position J minus 1, then equal to our right-hand side, which is the R times temperature at J plus 1 at position at time N plus 1 minus R 1 minus 2R temperature at position J of N, and then plus R at temperature at J minus 1. Okay. So we'll start with the left-hand side first here where we have the N plus 1s. So left-hand side. And we want to do is basically plot out these diagonals that we showed earlier here on the whiteboard. So we do the negative R, the 1 plus 2R, and the other negative R on the right hand side. So let's just do one by one. So let's do the first diagonal. Okay. So this would be MP dot R. So we need to put these in rows. And the first one will be R. What is it? NPR of NP full. Yeah, NP full. And then this would be it would be first negative R of M minus 1, N minus 1. I'll be N minus 1. Because remember, N minus 1 is what's in the middle. So we're representing this here, N minus 1. So N minus 1. And of negative R. And we will start off, and the right-hand side will be 0. Okay. Second diagonal is the 1 plus 2R. Okay, so we can do it from like the temperature T. So remember, we did negative R first. So it'll be negative R, and then everything else will be 0. 1 plus 2R, you have this in the middle, and then 1 minus R. Okay, so the second diagonal is the 1 plus 2R. That will be equal to NP dot R. Actually, it would not be equal to NPR. It would just be 1 plus 2R, 2 times R. This would be NP full. And then of N just by itself. And then 3, the third diagonal is NP dot R of NP full, NP dot full of N minus 1. I need capital N minus 1. And then of negative R. And this time the 0 will be in front. Okay. So this should be 0 and this. Okay. Shift enter. Invalid decimal. Invalid decimal. Anyways, so these are our 3 diagonal equations. And what we want to do is we want to stack them into one row, basically. So what we would do is we would use NP-V stack. So it just takes all these equations and stack it into one. Okay. So what we would do is you will take this NPR, put it in here. Okay. And then the next, we'll do the next one. So NP dot full for second diagonal. And then we would do the last one for the third diagonal. All right, we'll get rid of this. Okay. And now this is our left-hand side equation. I mean, our left-hand side represented in the equation. So we shift enter. Oh, cannot intercept. What is the problem? Okay, cannot intercept -2 as a data type. -2. Where is that at? Let me see. PR full and -1. I'll be right back. Let me see what the problem is. Okay, so I looked back through my notes and it was kind of a couple issues. So for the zeros here that we have in the full to complete the a row, we actually put them in the wrong place. So this NP of full, the N minus 1, this is correct here, and N minus 1, it shouldn't be inside here. And the 0 should actually be represented on the outside right here. Okay. And then same for the first NP dot row for the left and the left negative R, the 0 should be over here in the beginning before we get to the NP of full of N minus 1 to negative R. Okay. And then I'm going to do this so we can fully see what we're working with. Okay. And then I think this should be good now. Let me check. V-stack. Let me shift enter, see that works now. No, I think what was the last thing? There was another issue that had to get fixed as well. Oh, was this? So our N still has to be in front. We had the right idea, but our N still has to be in front. Okay. So now shift enter. Now we get our V-stack. We get our we get all of our equations. We get all the left-hand side, put it into one column. So here we go. This is exactly what we wanted. All right, perfect. So now let's do the right-hand side. All right. So right-hand side is a little bit more trickier. since this would be our final temperatures for the bar, so we want to, the main thing is that we want to keep appending and reiterating what the new temperature is after each after each run of temperature throughout the loop of a given time. So what we'll do is that we will first put a T history. We'll say this is equal to our T initial. So we just have a starter, like we have a reference. This T history will be the basis of what we will have, like our final temperatures that will keep getting appended over time. So this will be our what we'll use at the end that will show all of our temperatures throughout a given period of time. Okay. So we want to start this off at T initial, which we have up here. Start putting down our right hand side now. So we will start with a for loop. So for I in range, and for our prompt, it said to give 100 time steps, 100 time steps. We'll start with our temps. So our temperatures will be equal to, initially we would take the left hand side, right hand side, and we'll take, so we do our T left. So if we're representing the block, we're just trying to represent the block here. So we do our T left, our T initial, and our T right. All right. And for here, since we don't want, because we're using T initial a lot, I don't want, and we don't want the T initial to get confused with other stuff, we will actually use T initial. We represent T initial as T old, so our old temperature, because it will change over time. T initial is equal to T old. So we'll use T old in here. Okay. All right. So next, we want to actually put this entire right-hand side equation in. Okay. So we would say we'll use this B. B is equal to, so let's start. So we have R times temp T, temp T, uh, of T, temp T, what is it? Temp T. Oh yeah, so this be temp T at, so we know this is a set of +1, so we want to start at 2. Since usually we will start at, in the middle will be 1 colon -1 to the end. So we will start at the position 2 because we have a +1 position step. And we'll go all the way to the end of the block. Okay. Plus now be 1 minus 2 times R. R. And then this would be at times temp T. Now we're in the middle of the block. Position, we'll say we're at position 1 here, position 1 here. So this would be 1, call it -1. All right. Plus R times temp T. And now we're minusing. So taking a step backwards. So we will do to the beginning of the block all the way to the to the two spaces before the end. Okay. Well, a space before the end here. Okay. All right. And that should be it. All right. So this is now the right hand side represented. And now we do want to state though for, so at B, at position, we still have to say at position, the initial position at the end position. Okay. We have to state because we know we do know the temperatures already because we're putting the 40 degrees and 80 degrees on the left hand side and right hand side. We have to state that in our block. Okay. Because this is our representation of our entire block. But we do need to state at position 0, not the final position, that there's heating being put into the side of the blocks. So we say at position 0, our first position, this would be equal to T left. All right. And our final position, this will be equal to or T right. And I'm sorry, I actually explained this wrong. So, and this would be to the second mission all the way to the end block. We will have this represented here as from here, this position here, all the way to here, the block before the end. And our last block will be from the beginning all the way to here. Okay. All right. So now after we have that, we are set to go. All right. So now we'll use the linear algebra that we stated earlier. So we do our new temperatures is equal to NP dot linear algebra, which is stated right here. I put it here so you guys have explanation. But basically, the solved bandit is a sparse. It basically makes a sparse matrices for us because we need a sparse matrices. This is basically what this is here. So sparse matrices. So we're just inputting sparse matrices and putting our equation into the sparse matrices. So we need to have a LRU, which is our integer number, our non-zero lower or upper diagonals. And then we just need to input our two equations that we're using, or two functions that we're using for the sparse for the linear algebra solver. Okay. So linear algebra dot solve found banded, and we'll first do a 1-to-1. This would be 1-to-1 for our non-zero lower upper diagonals. And then we would just import our, where is they at? Where are they at? Oh, I never named this. Okay. Good thing I saw that. So for our left-hand side, we would call these all of our diagonals. So it'd be a diax for all of our diagonals. So then now we put it here. So a diax. And then we were input. So we have our left-hand side, and then we were input our right-hand side. And that's it, ladies and gents. So this is really all we need for this. This is our left-hand side here, which is put in here. And we have our right-hand side right here, which is input in here. Okay, so we should enter, should be good. Tuple, our T left. Our T left does not support a tuple. Why does that say that here? We'll fix that later, but we will continue with this. So like I said earlier, we need to have our T history be appended for each time we have a new temperature that we run our series from, and we have a range of 100. So what we need to do is that we need to append like a T history dot append all the new temperatures. Okay. All right. So now we have every single diagram, we have a new temperature. It'll be appended, so we get an updated list of what the new temperature is. So we have we will have a whole entire list of what we started off with, our temperatures, and what we ended with for our entire block. So this is literally exactly what we need. And then we will put T old is equal to T new. So this will be a copy. So we basically are saying we can now, every time we get a new T old as well. So we have our TO representing as our T initial. So it'll be our 20 degrees. So our TO will now get updated as well every time we have a new temperature inside the blocks. Okay. So the T history just saves all of our prior runs. And then it'll be listed all of the prior runs that we had. And then our TO will actually update, and it will update our intermediate temperatures with our new temperatures as well. And we want to do a copy of this. And we'll do a copy here and a copy at T initial. And the reason why we do this is that our initials, like our T initial and our T new, actually don't change as well. Because if you just left it as T new, like our TO is equal to our T new, when your TO changes, your T new also changes. So let's say besides TO, we had like T1 is equal to A, and let me write this down. So let's say we had T1 is equal to A. All right. I don't know why I did that. Okay. We have T1 is equal to A. And then we say that T2 is equal to B, is equal to T1. So now we know how to do this. So don't start tweaking. We plot T2 is equal to A. Okay. Well, if we state that, let's say T2 is now equal to B. All right. All right. When we do this, our T1 now, okay, well, our T1 will become B. Okay, our T1 will be, so it'll replace what we initially had. So what the T copy does is that it keeps what we already had initially and doesn't change over time. So it's a copy of what we had. All right. So now that we have that, we shift enter and T left as a tuple. Um, why does it say that? It should be fine. I don't know why it's saying that. As a tuple, this tuple object does not support item assignment. Let me check what the problem is, and I'll be right back. Okay, so I came back to my notes, and I figured out I messed actually a decent amount of things up. So the one thing first is that for the rows, I actually put them in parentheses and these be in brackets for the matrices. Okay. So that was the first one. The second one is that for our B initial and our B for our last point, we forgot to multiply by our R's. Because remember in here, you see our last 2 points. Remember when we get to the far end to the left side and right side, you have a negative R of TO and a negative R of TN, which you have to add to the other side. So this is what we have to do here. I totally forgot. Well, that's actually not the reason. The reason why is because our first and our last values, our first value and our first temperature in the beginning block will be 40, which we have to represent there. It'll be also times R. So, well, actually, yeah, basically literally what I said, yeah. Because remember from the matrices, you have minus RTO plus RTO, e minus RTN, and you have to add it to the other side. So this would be the addition of it right there. But yeah. And then the last thing, I don't know why I said it, but I put it as MP. It should be SP. That's the reason why we have it here. I don't know why I messed up, but yeah. Now we should be good. All right. And now from here, we'll put in our last temperature. So we'll collect all the temperatures and we will do MP. I think is it V stack? I'm pretty sure it's V stack. Yeah, it's V stack. And we do lengths of T history. So it pulls the data. It's for our plotting. No, it's MP.C. It's just columns. It's just we're just putting in a column. That's what it was. It says T history, and comma, the middle. What is it? Is it MP? Try to remember. MP dot array? No, I don't think it's MP dot array. Is it a range? MP dot arrange? I know there's a no, I think this is MP4. MP4. Yeah, MP4 T history. Yeah, a T history. And then oh yeah, MP and then yeah, I remember. So it's length of T history and then comma. Can I please go over? Thank you. And then of T right, I mean T left. And then it's MP dot full. And then we have length of T history of T right. Okay. So it's taking the day all what is it? So lens is it's taking turn the number container. So it's turning the number in T history, and then we start off the temperature to the left. All the T history. Okay, so all the numbers inside the middle, and then the number of the T history on the right. Okay, let's think this is right. Okay, so one argument. Okay. So that means is it? I'll be right back again. Let me see what this is for the last one. Okay, so I was on the right path. I was on the right mindset. The thing is, so this would be NP full here, NP full, and then the number size would be the lens of the history, and then the next statement for the full would be your T left. Okay, so then that will give you the NP full, and then your next statement will be a V stack. So I said these out loud, I just didn't put in the right place, but a V stack of all your history in the middle. And then the last three would be the same thing, NP out full for your lens, and then to the right, and then to your right. All right, and now I think that's correct. Put extra parentheses. C class, I think it because it has to be bracketed. Is it column? Perfect. So now from this, we will plot out, we'll plot this out. So I actually, kind of cheated a little bit. So I was kind of lazy. And I just took what we did for our last statement, what we did for part B, for our plot, and just copy and paste it here. We will make some changes though. So two things that we will not need is that we don't need this because we're not doing the regular heat diffusion when we're doing cracked Nicholson. So we don't need that. And we also do not need this as well. Okay, so it said we will replace this with the X plot for our X diagram. And this will be NP dot arrange. Arrange. And now we would in the bracket we'll do our T shape. And for our T shape, I'll plot it here so you guys know what our T shape looks like. T shape is the shape of our temperature. So how the amount of numbers of temperatures we have. Oh, I spelled shape. I didn't even spell shape. Okay. So we have 101 values in 22 time events. Okay. So that's the number amount for our time is 101. So for our T shape for our beginning, we will put for our X plot, we have 22 values. So that'll be T shape of 1. Okay. That's how many times, that's our time, that's how many times we have of the block, of the heat depending blocks for the block. I can't talk. That's how many block spaces we have in our uniform block, and then our 101 is the time it took for our shape. Okay, so that will be actually representing here. So this would be T shape at position 0. So we have T shape position 1 for our X plot, T shape at position 0 for our range. So it'll be range of 101 for our time for the shape. And then what we'll put here for our X is that we will put in X plot. And then for our T, I think our T is correct. Yeah, I think our T is fine. So now we should be good. Let's give it a shot. Numpy, I spelled shape wrong again. Oh, geez. Okay. Let's try this again now. Okay, we have a graph. It's not correct though. So what is the oh, because we're supposed to have, like we say in our statement, we need 10 step intervals. So let's put this down. Because that was only 1. So let's do 10 step intervals. Still not correct. Okay. Let's see the problem here. I think it has to do with our temperature here. I'm pretty sure actually it actually does have to do with our temperature. I think our Y is wrong because the Y shouldn't look like this. It should be, hmm, what would be our Y? Wouldn't it wouldn't be B? It wouldn't be, would it be T history? Maybe T history. No, that is also wrong. What would be our Y in this case? We have our T shape. It's not temperature because we put that for our X plot. For our Y, well, we have it goes to 40 to 80. Is it temp T? Interesting. Okay. Well, we got something. It looks way better than we had. It's still incorrect. But this does look better than what we had. I'm gonna check from last time my notes to see what our Y should be, and then that'll be our final plot for this array here. Okay, so the last thing we need to do is we put T and we use our I statement. So for I, for our temperature of I, and then of the entire block. Okay, so for our whole temperature of our block, for we will put in the I statement in here for our bracket, and then for our next term we would do for I for the entire block here. Okay, and now this should be correct. Yes, perfect. Um, I think there just still is something messed up here because there shouldn't be points. Yeah, there should not be points. Um, yeah, there should not be points. Why is there points here? This has to do with the crafting, I guess. Um, okay, so I see what the mistake was. So last thing we forgot to do is that for our two statements here for our first point and our last point, we want our B's, our temperatures for the left and right to keep being applied throughout the block, not just for the first and last time. So we want to keep adding these for the entire block as it runs 100 times. So we need to put a plus equal for this statement for both statements. So now the B initial and B the 40 and 80 on each side of the block will now actually be added each time we run every 100 times. So now it should show up on the plot as well. I think that's all we needed. Yeah, perfectly. So yeah, here we go. This is now the correct plot for our Cock-Nicholson heat diffusion equation. Yeah, there you go, guys. I know this is a lot. It was more than you expected, but it wasn't that bad. Hopefully this helps you guys out, and I will see you guys in the next video.